So I want to address a very simple question today, and that is whether we can identify potentially active faults. Obviously, we will avoid them if we can. Now, this is something we do all the time in practice, but we've never done it at the scale of a state, and we've never done it with the specific purpose of trying to reduce seismic hazard by actually, affecting how field operations are being carried out. I want to draw your attention to two posters on Friday, one by Richard Alt on the stress map that I'll be showing, a new stress map of Oklahoma that's almost finished, and one by Randy Walters, who's talking about site characterization protocols as well as risk assessment protocols. So three basic points I want to address. The concept of critically stressed faults is sort of widely known. I want to talk about it in specific regard to the question of triggered seismicity. Talk just a little bit of ongoing work that Walsh is doing on correlations in more focused areas between wastewater injection and seismicity, and then come back to using the stress map to say why some faults are important but most are not. So you're all familiar with the fact that we have earthquakes everywhere through intraplate areas, and there's a long history of things, small perturbations such as associated with the impoundment of reservoirs, triggering seismicity in areas that have relatively little background activity, such as the Canadian Shield, those are the red dots that you see, or the Indian Shield. Basically, stresses are high everywhere. The rate of seismicity is not an indication of stress in the crust, it's an indication of how fast the crust is deforming via brittle faulting in the upper crust. So now when we look at cases like the Guy, Arkansas sequence, what's really important is the fact that injection in the sedimentary rocks above basement appear to have triggered faulting that extends down into basement. And to me, the issue of seismic hazard is really, very closely tied to whether or not, there's a potential for triggering faults into the basement. Now, in the Prague earthquake sequence, this is Katie Karanan's work. The former slide was from Steve Horton. It's really not clear, I think, whether or not the injection into the Wilzetta well located about there, or injection in wells surrounding the fault, or whether this was a natural earthquake. It's really hard to answer that question. But if it was an injection induced, it was another case in which injection into the Arbuckle Formation, which Austin was just talking to you about, clearly induced faulting down into the basement. This was a 5.7. The largest earthquake was 5.7. It was about 4.7 in the case of the Guy sequence. And earthquake scaling relations simply showed to get earthquakes of the scale of 4.7 to 5.7, you're dealing with slip-on faults that are 10 kilometers or tens of kilometers in extent. You have to be involving basement faults. Now, we've been looking at the hydrologic properties of faults in crystalline rock for a long time, and one thing that comes right out from looking at literally thousands of faults is that faults that are active in a geologic sense, in other words, have a high ratio of shear to normal stress, in fact, a ratio of about 0.6, a ratio that's equivalent to the coefficient of friction of faults, those faults tend to be hydrologically permeable, whereas old dead faults tend to be hydrologically impermeable. So in these four boreholes, the blue is the deep KTB well in southeastern Germany, the large symbols indicate hydraulically conductive faults as detected with thermal anomalies, and the small symbols indicate faults for which there is no thermal anomaly, and therefore it does not seem to be hydraulically conductive. And when you actually compare the two distributions, you can see that the peak for the hydraulically conductive faults is for a coefficient of friction, corresponds to about 0.6, the coefficient of friction of common rocks. So if a fault is active in a geologic sense, it's hydrologically active as well, compared to the matrix or compared to dead faults. So John Townend and I compiled these data. What we're showing is permeability on the x-axis, corresponding depth from deep wells. Yellow corresponds to matrix permeability, and the colors are the rates at which earthquakes are diffusing and other indications of bulk permeability. So the bulk permeability tends to be on the order of about a millidarcy, about 3 to 4 orders of magnitude higher than the matrix permeability of these crystalline rocks. A very nice paper by Zhang et al. Actually looks a lot like the kind of developing conceptual model we have for what's happening in Oklahoma. Injection into the Arbuckle Formation causes pressure to spread out with time, and of course the permeability and the injection rates control exactly how that's done. And then they just put, a fault in with high permeability at some distance away from the injector, and of course when the pressure reaches that fault, because that fault is so much more permeable than the other rock, the pressure changes in that fault, and if it's a critically stressed fault, you can get a triggered earthquake. Very simple, but what it does is it says that the earthquakes are going to occur where the faults are, and the injection is not necessarily in exactly the same place. So it's often not possible to simply connect the dots as we do in most cases where we can clearly identify triggered seismicity. So this is a map that Raul has prepared. In red you see all the earthquakes that have occurred in the last 5 years. Yellow dots are 34 years of previous activity, and black is just the high rate injectors, more than 100,000 barrels a month. As Austin pointed out, there's nearly 10,000 active injection wells in Oklahoma. So it's really, it's really a complex process. What we've been doing is working in each of the areas within those white boxes to try to see what the correlations are. And statewide, it's really hard to see what's going on. The seismicity began to increase, the red dots, magnitude 2.5 and above, very abruptly in 2009, as you've heard before. And this is the monthly water injection data. This is a data problem which has since been fixed, and we now have data through the end of 2013. So you can see the injection rates have basically doubled throughout the state over about a 17-year period. But the real question is why the earthquakes, occurred. The onset of the increased seismicity is so sudden and in these localized places, and this is what we hope to be able to tell you about soon. Wellhead pressure is largely irrelevant. That's because the Arbuckle is widely underpressured, and the reported surface pressure is basically friction in the wellbore. It is not an indication of pressure in the reservoir. Here's just one area that we've been working, which I just pulled out to show you when you reduce what happens. Here you can see the injection rate going up over a period of about a decade, and the earthquakes kind of starting in around 2009. And this is one of the areas where there really is not a good correlation between the location of the individual earthquakes and the locations of the injector wells. These epicenters are probably accurate to 5 or so kilometers, and that's a 50-kilometer scale. So it's often it's often difficult to identify a single source, and what's emerging is a picture that it's the cumulative injection in these areas from multiple wells and not single points that are causing the pressure changes inducing the earthquake. So you can't just say, don't inject above a certain rate. If that wastewater is distributed among other wells so that the average rate is low, right now it looks like it wouldn't change things much at all. So it's a cumulative injection in these areas in many wells, and we hope to be able to present that to you in detail in the near future. So why are some faults important and some are not? I've said we've done this in many places. Let me just show you one example from the Teapot Dome area where a CO2 pilot project was being planned. One site was in this area of the S1 fault. Another site was in the area of the S2 fault. We have very good wellbore data here and here. The stress state is essentially identical. And when we look at this S1 fault, what we can see is the stress orientation and the relative magnitudes of the stresses indicate that this fault is not likely to slip under any physically conceivable pressure change. In other words, you can fill the entire closure with CO2, which exerts a buoyancy pressure on the fault, but that can't induce faulting. And we can show that here in terms of, there's the fault, and there's what we're coloring there is the pressure change needed to make that fault slip. And because there's uncertainty in each of our parameters, the vertical stress, the two horizontal stresses, the pore pressure, even the geometry of the fault, we can go through this, through a Monte Carlo simulation and demonstrate, that to whatever degree of certainty you would like, the pressure change that would require that fault to slip far exceeds anything that's likely to happen. And just remember, you can't change the pore pressure any more than the magnitude of the least principal stress, or the formation will hydrofrac and the pore pressure stays at that value. So here's our new stress map. The world stress map had about 10 high-quality data points, and they're now approaching 100 high-quality data points. This is all data that's made available by private industry. The fault map is on Austin's map, I think it was the light blue color of the faults that are shown here in the sort of the rust color. What we see through most of the state is an extraordinarily uniform, roughly north 85 east direction of maximum horizontal compression. And Austin and Bob Herman and others have shown that almost all the focal mechanisms are pure strike slip faulting. And so it's a relatively, simple tectonic setting to evaluate which faults are likely to be active. Now, we can look at three places: the Meers Fault, the Nemaha Fault, and the fault that broke in the Prague earthquake. I'm not going to say any more about the Meers Fault. As Austin pointed out, it produced a magnitude 7 earthquake 1,100 to 1,300 years ago. It's interesting that there does seem to be kind of a rotation of the stresses in this area, and we hope to kind of fill this story out and understand the stress field better than we do today. If we look at the fault that broke in the Prague earthquake right here, we can see, and here's Prague right there. We can see we have a stress orientation right at the fault, and it's exactly the same as the stress orientations in the surrounding region. And this fault plane, which produced a right lateral strike slip earthquake, is exactly what one would predict. It's about 30 degrees from the direction of maximum horizontal compression. Now, in the January 2014 paper by Karan et al., which was a very nice paper, with the following exception. They speculated that the Nemaha Fault could potentially be reactivated by fluid pressure changes. The Nemaha Fault is a very big fault. It essentially runs right along the edge of Oklahoma City. And a large earthquake on that fault would have very dire consequences. Okay, it is a fault, but it's a dead fault. And if we look at the orientation of that fault with respect to the stress field, it's a very steeply dipping fault. And for those of you who are familiar with Moore circles, the fault normal is essentially parallel to SH max. You would have to raise the fluid pressure at twice the value of the minimum horizontal stress in order to get that fault to slip. It's physically impossible to do that. Okay? So, can we identify potentially active faults? I think we can. We need good stress data, but it's easy to obtain in these areas because there's been a lot of modern drilling, and I didn't take time to tell you how we do this, but it's pretty well established. So the data that's being routinely acquired is enough to give us a fairly good sense of what the stresses are. We need good knowledge of pre-existing faults. This is a lot harder to do, and as Austin pointed out, while we're working on this part of it, the state is working with industry on this part of it, and of course, we need to bring the two parts together. Right now, it looks like we may be able to do that as early as the end of January, early February. We also are very interested in the faults that extend down into basement, and as many of you know, that's a difficult thing to do, is to image faults in the basement, but hopefully the faults we care about, the active faults, are showing some expression in the sedimentary section. That is true. The fault that broke in the Prague sequence can be seen in 3D seismic data. The fault that broke in the Guy, Arkansas case can be seen in 3D seismic data, but it wasn't seen in either case until after the fact. Okay? The other thing we have to keep in mind is that the potentially active faults can be at some distance from the injection wells. And so this gets into the kinds of sophisticated modeling that we know how to do. The problem is we just can't constrain the models with the parameters that we need. And it's really regrettable, but this is something that's going to take a lot of attention and a lot of work to, yes, to build better models, but to populate those models with well-constrained parameters. I think that's the real challenge. And then, once we do that, we can make the kinds of predictions about, well, if you change injection rates, what's going to happen over time. Well, I alluded briefly before to the fact that the Arbuckle Formation is under-pressured. This is widely recognized and extremely poorly documented. Why is it widely recognized? Because people can pump into that formation at essentially zero wellhead pressure. So the weight of the fluid in the wellbore is enough to push it down into the Arbuckle. But because these are wastewater injection wells, nobody's taken the time to actually measure the pressure in the Arbuckle, much less its permeability and so on, the kinds of parameters we need in a good model. And it's very clear that injecting very large volumes into formations in direct contact with the basement is not a very good idea. Now, the work that Randy is leading at Stanford has many components, and I hope you see your poster on Friday. One of the components is a stoplight system. I'm obviously not going to read the fine print, but I do want to draw one thing to your attention, and that is it's really important to start adding geologic criteria to what in the past have been either earthquake magnitude or ground shaking criteria. So for example, when earthquakes start propagating into the basement, that's not good. Now, as everyone in this audience knows, we can only determine earthquake depths accurately with really good seismic networks. And I think one thing that has to come out of all the studies that everyone is doing on this question of understanding and better managing the hazard and risk associated with induced seismicity is we need to start obtaining much better data, seismic data, pore pressure data, and so on. And with better data, we can make better decisions about how to proceed into the future. Thank you very much.
We have a minute or so for questions for Mark. Ernie, repeat the question.
So yeah, the question was, if I had all the money in the world, I've got about 85 cents here, what would I do to better understand these processes? Well, let's just follow the idea of developing better models, for the seismicity in Oklahoma. You'd want to know where the faults are as accurately as you possibly could. You'd want to use the data available, and in most places, the data is pretty darn good for getting the stress field. Okay. The one thing we really don't have very good control over is the hydrologic properties of the basement, of the, even of the Arbuckle Formation. Looking back in time, the water injection data is full of problems, but you could probably get the big picture about right. So it really isn't all that complicated. You'd really want to, we all kind of know what's going on, but, how can you believe a model? So in a discussion, one of the oil companies said, well, we don't want to get into all this expensive modeling. And really, the modeling is not expensive. It's just frustrating because it's hard to constrain the models, and unless you can constrain the models, you certainly can't use them for predictions of how you should alter what's been done in the past to achieve a better, result in the future by just doing what you've done previously.